a Portland Community College mathematics telecourse. A course in arithmetic review, produced at Portland Community College. This lesson will not only assume that you have memorized the addition tables, which you used on the last tape, but that in addition to it you have memorized the subtraction table. That all we wish to do here is to examine the process of subtraction a little bit more closely and then to refresh ourselves on the matter. And the first part of this refreshing is to remind ourselves that in our culture we prefer to do our adding and subtracting in vertical columns. There are cultures which do it differently, but we like ours this way. Vertically, with the place value columns lined up. And if you need vertical lines to help keep things neat, that's fine. In fact, many people prefer doing their papers endwise like this. These lines, after all, were designed to guide us in writing. Frequently in arithmetic, it's more helpful to turn the paper this way. Have you ever noticed an accountant's notebook? They not only have lines going this way, but they do have lines going vertically as well. And if the professional finds this useful, then certainly we amateurs can too. Then you recall you can only subtract ones from ones, tens from tens, hundreds from hundreds, and so forth. Then you simply, using your memorized table, subtract. 3 from 5 is 2, 0 from 4 is 4. And some of you might recall that when you first started this process, rather than thinking 2 from 7 is 5, you thought 2 plus what will give me 7, which is 5. And you begin to realize that subtraction is, after all, nothing more than reverse addition. What can I add to 4 to get 8? And that's 4. Then eventually we twisted that around and just thought 4 from 8 is 4. And we're done. Basically, the problem is that simple, providing, of course, you have your tables memorized. But the words concerning subtraction is a different matter. People very frequently get confused on that, so let's take some common phrases denoting subtraction and look at them rather carefully. When we say 3 less than 9, or one number less than another, actually, when we write it mathematically, we're saying 3 less than 9. Do not write this first just because it came first. The word less, in effect, says that this is being subtracted from what follows. Now, if we use the word minus, 8 minus 5, then in that case, we simply write it as we come to it. And if we use the phrase difference between two numbers, we write the two simply as we come to them. So minus and difference, you write the numbers exactly as they appear in the sentence. But if you use the phrase less than, then in fact the numbers as they appear in the sentence are reversed mathematically. So be very cautious on that, particularly this phrase less than. And also, let's caution ourselves to be careful when we need to borrow. First, let's line these up vertically by place values, like this. Then remind ourselves we can only subtract places. So we want to subtract 6 from 4, but in fact 6 won't subtract from 4. A very common mistake is to reverse this and subtract 4 from 6 and write 2. But that's definitely wrong. You must subtract 6 from this. Since we can't, we recall the relationship between one column and the one to its left. Remember, 10 of these is 1 of these. Consequently, 1 of these, so if I take 1 away from the 7, that leaves 6, is 10 of these, so I'll add 10 back over into this column. Now we have 10 and 4 is 14, and 6 will subtract from 14 8 times. This process we call borrowing. Now in this case 3 will subtract from 6, so I do so. 2 will subtract from 2 0 times, so I do so. And I'm done. So remember the basic relationship. 1 in any column is worth 10 of the one just to its right. So I can always borrow 1 from there, which is adding 10 over in this column. It's as though I borrowed a $10 bill, changed it into 10 $1 bills, and added to the 4 $1 to get $14. A simple process if you think about it just a bit. And of course, in practice, we usually get our problems in verbal form. So let's say Mr. John North owes the Murphy Construction Company $4,035. He made payments of $1,085, $537, and $894. How much does he still owe, rounded to the nearest $100? A three-pronged problem. First, I could subtract each one of these payments one at a time from this, just as we would in a checkbook. The shortcut would be to add all these payments together first, like this, and of course total means I'm going to add, and if I actually add, I get $2,516 total payments. So we've done that much of the problem. But that total is to be subtracted from his bill, which was $4,035. So doing that, we get this problem, subtraction, which has the answer $1,519. But they wanted more than that. They wanted the answer rounded to the nearest $100. There's ones, tens, hundreds. So I look to the digit just next to it, which is 1. It's 4 or less, so I round down, which means that those are replaced by zeros, and at the rounded place is left as it is. So I can state that we owe the construction company roughly $1,500, rounded to the nearest $100. This problem illustrates that in reality, when you get a problem, it seldom is simply a subtraction or an addition. It usually involves all of the things at once. In this case, addition, subtraction, and rounding off. So usually it's not a matter of just doing this or that. It's a matter of doing a sequence of operations all within one story problem. Now, while reviewing our arithmetic, let's simultaneously begin to get ready for algebra, whether you will actually take a course in algebra or just use simple formulas or equations in business math, science, nursing, technology, or whatever it is. To solve an equation, look upon it at first as a sentence. It's saying some number, subtract 37 from it, will give me 59. What number will make that true? Now, in this case, where you're subtracting a number from this unknown one, you simply have to remember this fact. It's a simple fact of numbers that addition undoes subtraction. Look upon R as the amount of money in your pocket. If I subtracted $37 from it, what would I have to do to have your pocket back to where it was at the beginning? Well, I would have to add $37 back into your pocket, and I'm right back to where you were in the beginning. We'll call that sum number R. Okay, now, if I add to undo that subtraction, the rule that we're going to have is that we must add the same amount to both sides. So in this case, adding 37 to 59, we get $94. So $96. So $96 is the amount of the R originally. Now to check it, we would simply do what this says. 96, subtract 37, 7 from 16 is 9, 3 from 8 is 5, and it checks. In algebra, we would verbalize this rule this way. You may add the same amount to both sides of an equation. So let's review. To undo subtraction, we added. But whatever I added to undo that and get me to the letter alone, I had to do to the other side, which got me the answer. So when you see an equation where a constant is being subtracted from a variable, you undo it by adding, which isolates the variable, and you add the same amount to the other side. So these simple equations are very simple to solve, as is this next one. Reading this equation, it says I have some number. Now remember, a variable is simply a math way of saying some number. If I were to add to it $85, I'd have $208, using dollars to help us think. How much did I have to begin with? Well, if I added $85 to get back where I was, I have to subtract $85. So that's our fact. Subtraction undoes addition. If I subtract 85, I undo having added 85, which leaves me what I had to begin with. But if I subtract 85 from this side, I have to subtract 85 from this amount over here, because our equation says this whole expression is the same as 208. So doing that, I get that m is 123. To check that, let's do what this says. It says take m, which we're claiming is 123, add 85 to it, 208, and that checks with our statement. So remember, subtraction always undoes addition. So if you're trying to undo an addition to isolate the variable, you simply subtract. In algebra, we will simply say you may always subtract the same amount from both sides of an equation. So to undo adding, subtract the same amount from both sides. In our previous problems, to undo subtracting, we added to both sides. That's simple. Let's do two problems side by side. We wish to isolate the m. To undo subtracting 8, we add 8. That undoes that, leaving m. Adding 8 to this gives me 23. But if we wish to undo addition, we subtract the same amount from both sides. Subtracting 9 undoes adding 9, leaving me with the variable by itself. And subtracting 9 from 22, we get 13. Just that simple. You have a few problems like this, and it gives you a chance to review adding and subtracting, but at the same time begins to prepare you for algebra, rather slowly and comfortably, I might add. Don't allow yourself to be tricked into thinking that the letters used in algebra are either mysterious or difficult. They are neither. In algebra, a letter is simply a convenient mark to symbolize the phrase some number. So if I were to say something like this, I am simply saying some number added to 45. If I were to say this, I am still saying some number added to 45. And the same thing in this case. Some number added to 45, or the sum of some number and 45. What number? Well, as it's written down here, we haven't the slightest idea. Somebody has to tell you. Then why so many different letters? Well, we might want to use T for taxes, V for velocity, A for amount. So we simply pick the choice of symbols to help us remember what it is we're talking about. That is, what kind of a thing did we measure or count to get the number that this letter is going to stand for. And since the letter can stand for any number I want it to be, rather than always saying some number, we call the use of these letters in algebra variables. And obviously, the reason we call them variables is they can be anything you want them to be or anything something measures to be. So it varies from application to application. If, however, I take an algebraic expression for a single number, this is a result of an addition called a sum, and if I make an algebraic sentence like this, then we could, in a sense, figure out what A is, because now we're claiming something about this sum. We're saying, look, I have some number. If I added 45 to it, it would be 92. Now, if just thinking what's written here is sufficient for you to tell somebody what that letter is standing for number-wise, then just write it. There's nothing to do. But what the algebra rules are for is a way of getting from this statement to determining what this variable is through a more methodical method. And that method first introduced here is that in very simple sentences like this, that if I subtract 45, having added 45, this undoes that and gets me down to the variable by itself. But our subtraction law of equality in algebra says, fine, subtract anything you want from this statement on this side of the equation, providing you subtract the same amount from what it's equal to, or the other side of the equation. So subtracting here, we would get 5 from 12 is 7, 4 from 8 is 4. So we're claiming that my number here called A is 47. And if we wish to check, then use this number in place of the variable in the original sentence and see if the sentence is still true. See, this equal is sort of a mathematical verb to stand for is, could be, will be, should be, was. So this is A, which I'm now claiming is 47. When added to 45, we want to be 92. So if we add these, indeed it is. So you see, it's very easy to review our arithmetic while at the same time very comfortably getting ready for algebra. Of course, algebra proper will handle equations far, far, far more complicated than this, but it all starts from here. So at this stage, we simply want to think of this as doing something to undo that and isolating the P so that the sentence will read P, whatever P will stand for, is something. So we recall that to undo subtraction, you add. But our addition law of equality is now saying whatever I add to this member of the equation, that is the expression on this side, we must add to the expression on the other side of the equality. And on this side, this has the effect of undoing that, leaving me with only my variable P. Then on the other side, we complete our arithmetic, and we would get 9, 9, 2, 14. So now just reading the sentence back, we have my number P is 14,299. See, nothing mysterious about that. It's just a mark on a piece of paper to stand for a number which I don't know yet. and by maneuvering I can find out what it is. We could just as well, if we wanted to, have left a large box there with a question mark on it, and it would serve the same purpose, but after a while it simply becomes more comfortable to use a simpler mark, particular mark that stands for what I might be talking about, price, or whatever it is. You can see in a simple math sentence there is really nothing to do. Reading this says, some number here called r added to 3 is 8. What number would make this sentence true? Obviously 5. There is nothing to do. You didn't really have to subtract 3 from both sides. You can just read the sentence and just see that 5 plus 3 is 8. So there is nothing to do. Reading solves it automatically. However, as these numbers become more complicated, then it is no longer so obvious what the solution is. However, it might be obvious that if I add 2354 to a number, to undo that I have to in turn subtract it off to get back to where I was. But our subtraction law of equality says fine, subtract whatever you want from this member of the equation, providing you subtract an equal amount from the other member of the equation. Of course, that subtraction undoes the adding. Notice the thing we're looking at first is not the number. That's irrelevant temporarily. We're looking at this. We're trying to undo adding by subtracting. Then this is, of course, the specific that we're trying to undo. But it's the addition that we're undoing. So to undo adding, we subtract. Now at this point, let's remind ourselves where subtraction came from historically. Back to our abacus. Here's 5 in this column, 8 in this column, 7 in this, and 9 in my units column. And again, our ancestors did not think of this as 5,879. They simply thought, quite simply, 5 here, 8 here, 7 here, 9 here. So all they could really do is count digits, and not too far, just somewhat beyond 10, and store them on the beadboard. Now to subtract meant literally to subtract things, not numbers. So this said, take 4 beads away from this column. There's 2, 4, take them away. Now take 5 away from my next column. So 2, 4, 5, take them away. Then take 3 away from here. Take them away. Then 2 from here. Then tell me, after you've done that, what you have left. So you can see I have 3 here, 5 here, 2 here, and 5 here. But the reason we can do this mentally is that we have memorized a subtraction table, which is simply a memorization of what happened on our beadboard, sort of like memorizing a paper route. After a while, you no longer have to look at your route list. You simply look at your house and deliver the papers. So now we don't need this. We, in our heads, subtract 4 from 9 beads, know that we have 5 left. If we take 5 from 7, we know that we have 2 left because we have memorized our addition and subtraction tables. Another example. To undo adding, I will subtract, and only then do I concern myself with what number. This determines where I start. And our subtraction law of equality says, fine, just remember to subtract the same amount from the other side of the equation. This undoes that, isolating my C so that my sentence now reads C equals the results of this, but now we see we have to borrow. 7 does subtract from 9, leaving me 2, but 8 doesn't come from 3. So here's where our historical process of borrowing comes from. There's nothing there, so 1 borrowed from here leaves 3. Give me 10 here, which is now 1 plus 0 or 10. But borrowing 1 from there leaves 9. Brings 10 over here, and 10 to 13, 10 to 3 is 13. So 8 from 13 is 5, 5 from 9 is 4, and 1 from 3 is 2. Let's now look at that borrowing process on the abacus, and you'll see that it really is quite clear and simple. So on our abacus, this simply meant 4 beads here, none here, 3 beads here, and 9 beads here. Now subtraction meant column by column, remove this many beads. So if I subtract 7 beads, it's just a matter of counting. 1, 2, 3, 4, 5, 6, 7. Remove them, and I have 2 left. I can just see them. No subtraction to do. Just a matter of following the bead instructions, record the results. But this now says subtract 8 beads from here. But I don't have 8 to subtract from. I only have 3. So we remember now, if I take one of these away, I can put 10 here. But I don't have 1 here. But I can go over 1 more, take 1 from here. 1 of these is worth 10 of these. So 2, 4, 6, 8, 10. But now, once again, 1 of these is 10 of these. So 2, 4, 6, 8, 10. Now we can say take 8 from this column, and I have more than enough to get 8 away. So there's 2, 4, 6, 8. I've taken 8 away from this column. Now we want to take 5 away from this column, and I can do it. So take 2, take 4, take 5 away. Now I want to take 1 from this column, so take 1 away. Now record what you have left. Well, I have 2 here, 4 here, and 5 here, and that was the solution to our equation. Hopefully you might say, hey, I can do it easier on paper than I can here. Then that's good. That tells you this lesson is going well. So, practice, become fluid. And this is your host, Bob Fennell, until our next lesson. Good luck.